Some questions about this problem, and so I wanted to make a brief guide to how to approach it. And if you have any questions after watching this, please ask. So what we're trying to do here is the top of the problem says that the energy for a one electron system can be determined using this equation, where N2 is the final state and N1 is the initial state for the value of N in the atom, the one electron system, that is. And for some reason, I could not get F and I, final and initial, to show up inside Canvas, so I went with 2 and 1 there. But this is final and initial, and this is an equation we've seen before. J is joules, the units, Z is the atomic number, and it's squared. And what we're going to do is we're going to end up filling in what I'm calling a ladder energy diagram with energy levels for each point. Before that, I ask you to write out the first ionization energy reaction for helium. And ionization energy reactions are something that we've done before. In this context, I might as well do it. So helium gas goes to helium plus 1 plus 1 electron. And then it says, underneath each atom or ion in the reaction, write out its electron configuration. Well, the electron configuration for helium is just 1s2. If you take one of those electrons away, here we have 1s1. And you can see that down here, we have helium 1s2 and helium 1s1. And so really the difference between these two is the ionization energy of helium, and that's listed up here, and it's sort of cut off on this my printouts. But that's the energy difference between these two. And as I draw the arrow down, I have a negative sign here because it's going down minus 2372 kilojoules per mole. And this state right here at the very bottom has 2 electrons in it. And so for 2 electrons, we cannot use this equation. But here we have 1 electron, all the way up until helium 2 plus has no electrons. And what you can do, though, is for all of these, you can use this equation to find the difference in energy. For example, if you wanted to find the difference in energy between n equals 1 and n equals 2, you would plug in, well, depending upon, let's say, we start at 2 and we go to 1. We would put n1 equals 2, n2 equals 1, and we could calculate the energy in joules per photon, convert that into kilojoules per mole of photons, or since this equation couples the idea that an atom absorbs energy in the form of a photon when the electron moves away from the nucleus. The photon is taken in and the electron moves. So we've used the energy from this equation not only in joules per photon, but also in joules per electron, because a photon and an electron are both involved in this process. Now, I think the example I've given here is when n equals 2. And here, when the electron has left the atom, n equals infinity. We've also got n equals 3, n equals 4, and n equals 1 down here. But if you go from n equals infinity as your initial state, 1 over infinity squared being 0 here, down to n equals 2, but 1 over 2 squared, you get 1/4. This is helium, so it's 2 squared. Anyway, you plug the number in, you convert it from joules per photon or electron into kilojoules per mole, and you get the number 1313, or minus 1313. Since we started up at infinity, we went down minus 1313 kilojoules, and that's the energy of this level. And when doing calculations of this sort, if you start with n equals infinity and we've defined that as 0, I would just use n1 as always infinity. Then this part cancels out, and you're just calculating the energy for each of these levels. There's lots of ways to do it, though. If you were to do n equals infinity to n equals 4 and just measure this, and then 4 to 3, and then 3 to 2, and then 2 to 1, you would keep getting the same answers just by adding or subtracting different numbers. But you can by just getting all the way down here, and let's say this is, I don't know, minus 10,000 by the time you get down here, then this would be minus 12,372 because it's minus 2372 lower than whatever you get for this number. And that's a brief tutorial on how to solve this part or this problem in particular.